Chapter 5 is initially going to seem a little bit like a shift from things that we ended in Chapter 4. We ended Chapter 4 by looking at this idea of antiderivatives. And so this is going to seem a little bit like a departure from that, and it is. Eventually, this will all come full circle, and we'll get back to that notion, and we'll tie these different concepts together. But for right now in 5.1, our primary objective is going to be to look at how to approximate the area under a curve. But before we can really get to that, we need to review, I think review for most of you. Some of you perhaps haven't seen some of this summation notation, this big capital Greek letter sigma. So that's what we're going to start with here. So as we look at this sigma notation, we have this big Greek letter sigma means the sum of. And so what this notation is saying is we're starting at a lower index of 1. So that's this value right here tells you you're going to start by subbing in 1 into whatever is inside of this sum. And then the big Greek letter sigma means then you are going to add, and then you're going to go up by increments of 1. So then you would go to a sub 2, and then you're going to add, and you're going to go to a sub 3. And you're going to continue this kind of going on all the way until you get to your upper limit of right here. In this case, until you get to this a sub n. So this is what the summation notation tells us to do. All right, so now let's look at just a couple of basic properties of sums. And the first one here says that we can, essentially it's going to look like the distributive property or factoring out a constant multiple. But let's write this out. So we start by subbing in 1, so we would have k times a sub 1, and then we would say plus k times a sub 2, and then we would take that all the way up to, we get to k times a sub n. So again, we're subbing into whatever is inside that summation notation. Well, if k is a constant, that means we can factor out this constant. So we can factor out this k from all of the terms. And then what we're really left with here is this constant multiple, and that sum is simply the sum as I goes from 1 to n of a sub I. So what we have here says that if you have the sum and there's a constant multiple, you can factor that constant multiple out in front of that sum. Next one. So let's take a look at what we have here. So we start with subbing in 1. This time, when I sub in 1, the first term, if you will, itself is 2 terms, right? So I start by subbing in 1, and I get A1, either plus or minus B sub 1, and then plus, then we go to 2, so A2 plus or minus B2, and then plus, and we would continue this all the way up to, we get to a sub n. So a sub n plus or minus b sub n. All right, well, if we reorder, we're adding and subtracting a bunch of terms, we can reorder those terms. So I could put all of the a terms, so I could have the a1 plus the a2 plus the all the way up to the a sub n term first, and then I could have my plus or minus b1 plus or minus b2 plus or minus all the way up to plus or minus bn. Well, if it's addition, it's no big deal, but if it was subtraction, we would have to think about factoring out that negative from all of the b sub I terms here. So we could say plus or minus, and then we could factor out, if it had been subtraction, we would factor out the negative from all of those b sub I terms. And then what we really get here is the sum as I goes from 1 to n of a sub I plus and minus, plus or minus, the sum as I goes from 1 to n of b sub I. So what this is telling us is essentially we can take a sum term by term. So we'll say it that way. All right, let's write out a couple of sum formulas, some formulas. So this first one, if I start and I say, okay, I'm going to put 1 in, well, there's no i's in this expression. It's just this c. So then when I put in 2, it's still c, and then all the way up to the nth term is still c. So I would be adding c n times. Well, that is simply the definition of n times c. So the sum, as I goes from 1 to n, if you sum n of those c terms, we end up with n times c. Okay, let's look at another one that we can kind of think about and reason our way through here. So on this one, if we were to add 1, add 1, 2, 3, all the way up to, and the second to the last term would be n minus 1, and the very last term here would be n. So if we were to add all of those up, if you think about what happens on kind of grouping these, if you added together the 1 and the n, that would add up to n plus 1. And if you added together the 2 and the n minus 1, that would also add up to n plus 1. So basically it's this idea, right? If you were to add up, let's say, a bunch of numbers, maybe like 1 to 6, right? So if we were to add up 1 and 6 would be 7, 5 and 2 would be 7, 3 and 4 would be 7. All of these pairs add up to n plus 1. And then if you think about how many of these you would have this n, which in this case is 6, divided by 2, you would end up with 3 of those 7s, and then you would have 21. So that's really what this sum formula is going to look like. It's going to be n, oops, I didn't mean to do that. It's going to be n times n plus 1 all over 2. So this is going to be our n times n plus 1 divided by 2. So the n plus 1, that's like the sum of the pairs. In my example down below, that's like the 7. And then the n over 2 is kind of the number of pairs. So that's just one way to kind of think through that one. Kind of makes some sense there. And then the last one I'm just going to jot down for you. So the very last one here. So these are just some formulas that we may need from time to time. And the last one, the sum of the squares. So this would be the formula for the sum of 1 plus 4 plus 9 all the way up to n squared. There's a formula for the sum of the squares. That's going to be n times n plus 1 times 2n plus 1 all over 6. Okay, so this is our formula for the sum of the squares. All right, so let's take a look at some examples here. First, or just one example probably that we're going to really do here. So let's take a look at an example. So the sum as I goes from 1 to 10 is what I meant to say. So the sum as I goes from 1 to 10 of, and we're going to have I squared minus 3i plus 2. Now certainly we could sub in 1 and then sub in 2, and we could add up the values we would get from this trinomial every time, but I want us to evaluate this with properties of sums. So here's what we know. We know from one of our properties up above that we can take, if we have a sum or difference, we can take a sum term by term. So that's what I'm going to first write out, is taking this sum term by term. And then from, again, one of our properties of sums, we know that we can take a constant multiple out in front of that sum. So in the second term, we can think about that constant, the k in this case, being a 3. So we'll pull that out in front of our sum. And now we can use our sum formulas. So here's what we now know from our sum formulas. The sum of the squares, that's this last one that we just did, the n times n plus 1 times 2n plus 1 over 6. N in this case is 10. So the first one is going to be 10 times n plus 1 would be 11 times 2n plus 1, that's going to give us 21, all over 6, minus 3 times, in my second term here, the sum of the i's, that's the second formula in the list above, the n times n plus 1 over 2. So that's going to be our 10 times 11 over 2. And the last sum formula, that's the last term here is the first sum formula up above, just the sum of a constant. That's just n times that constant. So in this case, 10 times the 2. So I'm going to save us the arithmetic, and this all comes out to equal 240. So there's a few of our sum formulas we need to be aware of. All right, so now what we're going to start to look at is this idea of how could I estimate the area under a curve. So if you think about this picture in the lower right hand corner that you have here, let's see if I can slide this up. There we go. So if I think about, suppose I worked for a company, this company has all these windows, and maybe it's my task to, maybe I'm buying some sort of UV protective screening or something, and I'm going to apply it to all these windows that you see in this picture. And I need an estimate for the area of all these windows, because this new UV shield, let's say, it's a price that's given like per square foot in terms of the area. So it's a way to think about, as an opening example, area under the curve. So if we were in class, we'd chat a bit, and I'd ask some of you, kind of looking at this picture, it's pretty suggestive that you have a bunch of rectangular panels. And so we might go about that by approximating the area. So we would probably say, oh, I bet I could, approximate the area using rectangles. Now, when we get to the very top of those rectangles, obviously it's curved up here, but maybe we still just think about estimating some of these. So, maybe we take and we just say, okay, yes, these aren't going to be rectangles at the top, but maybe if I'm just coming up with an estimate, maybe I just sort of think about them as being rectangles, and I just make a rectangle at the top. And so that's what we're going to think about doing as we move forward here. Okay, so we're going to be looking at estimating the area under these curves, and we're going to do that by computing some areas of an easy area to use that we know is areas of rectangles. Now, there are going to be a number of different kind of ways that we could approximate the heights. So as we look at this first example that we see here, it says 2 common approaches for using finding heights of rectangles are either left endpoints or right endpoints. So as you look at these pictures, kind of really let's emphasize here that we have a region that has been divided into what looks like 5 rectangles. And in the first picture, they went to the left edge of each of these and just made that the height. And you can see sometimes we get maybe too much area and sometimes we get too little, but they use left endpoints in the first picture. In our second picture, we said, well, left is fine, but we also could have used right. I could have went to the right edge of each of these rectangles, and then where that intersects on the function, that could have been the height. So that would have been fine as well. Again, some rectangles give us too much and some rectangles give us too little in terms of the area. And we have a name for each of these. So if you get a rectangle that is underestimating your area, then that is what we call an inscribed rectangle. So if you get an underestimate, That is an inscribed rectangle. And so if I look up above in the first one here, this would have been an inscribed rectangle. It's an underestimate. There's too little area. And then the same on the last two in the left endpoints. Those are both also inscribed rectangles. Over on the second picture with the right endpoints, it's the second and third rectangles that are inscribed. So inscribed, think they're kind of under the curve. Let's put it that way. And so underestimate because they're under the curve. Now, if you had a picture of something where it was entirely inscribed rectangles, so all inscribed rectangles would give us an underestimate, or what we're going to call a lower sum. That'll be denoted with a lowercase s. Now, if I was to look at the rectangles that give us an overestimate, so those are going to be rectangles that are over and above the curve. Those are called circumscribed rectangles. So when we go back up to our picture, in the first one, it's the second and the third. Those go above and beyond. They're over the curve. They're giving us too much area. In the second picture with the right endpoints, it's the first and then the last two that are circumscribed. So again, if you had a situation where all of the rectangles were circumscribed, then you're definitely getting an overestimate on the area, and that would give you, so that's going to be an upper sum. All right, so let's take a look at the pictures that you see here, and let's highlight the rectangles that are used in the lower sum and the ones that are used in the upper sum. All right, so if I had, in this case, it's a parabola-ish type of shape. It looks like I have, 6 rectangles all together. And so the lower sum in this case is going to be the ones that are inscribed or give us too little area. So here's my inscribed rectangles. So on the first two, notice it is the right endpoint that's giving us the inscribed. But that doesn't stay. Also on the third one it does. So right endpoint is giving us that inscribed rectangle. But now as I move into the last three, it is now the left endpoint that is also now giving me an underestimate. So now, as the function turned into increasing, it is the left endpoint. So there's a relationship here that we're kind of starting to realize. So if now let's also look at part B, and let's highlight the rectangles that give us an upper sum. Okay, so the upper sum is the one that's supposed to give us too much area. So in the first rectangle, it is the left endpoint that would be giving us an overestimate on that area. Again, the next one, a left endpoint that's giving us too much area, and same thing on the third. But now as I go into the last three, it is the right endpoint that is giving us too much area. Right endpoints, overestimate. Right endpoints, circumscribed rectangles. So again, that behavior of which endpoint was either giving us too little, or in this case too much area, changes depending on if the function is increasing or decreasing. So if we focus on regions of functions that are increasing, so that means if I look at this part of the curve right here in each of our examples where the function is increasing, the lower sum, so that was part A, what's in blue, so the lower sum is coming from using the left endpoints. So when the function was increasing, the lower sum is from left endpoints. When the function is increasing, the upper sum, so the picture in part B, the upper sum then came from the right endpoints. So when the function's increasing, the upper sum comes from using right endpoints. Now this switches though when we look at where a function is decreasing. So if we look at now the first part of the curve, so now if I look at the first three rectangles, so again, now we're focusing on these three rectangles. In the first picture, the first three rectangles are where the function's decreasing, and that lower sum actually now came from the right endpoints. And then if we go over and we look at the picture on the right, where the function is decreasing, so the first three rectangles, the upper sum now came from using left endpoints. So, you might be asked for any of these types of situations, right? They may say, find a lower sum, and you might have to think about, which type of endpoints is that going to be, depending on if we're increasing or decreasing. They may just say, use left endpoints, and that could be any combination of it being either a lower or an upper. So sometimes they'll just say, use left endpoints or use right endpoints. Sometimes they may ask you to find the lower sum or find the upper sum, and then you have to think about the increasing or decreasing behavior of the graph. So the one last thing I want to talk about on this video before we get into kind of the formula and the computations on the next video is, well, what would happen if you notice in the example that I just did up here, this function changed behavior right at an endpoint, right? Change behavior meaning from increasing to decreasing and vice versa. It was right at an endpoint. Well, what happens if that wasn't the case? Well, then it might just come from some points in the middle of that interval. So again, suppose that in this first picture, suppose this was my interval. Like this was, I'm in the middle of the graph and I'm at some left endpoint and some right endpoint, or over here, same thing, back up to my picture, sorry. Some left endpoint, some right endpoint. So here we go. So what would happen would be the min value this probably isn't going to happen so often for you in most of your examples, but a minimum value could be somewhere in the middle of an interval if that increasing, decreasing change happened in the middle of some interval. So here again, if this is, my fourth rectangle or something, and we're asked to do an upper sum or a circumscribed rectangle, it could come from some point in the middle of that interval. So this could happen in theory, of course, it can happen. I don't think this is probably going to come up so much for you in terms of homework or anything like that, but it's just something that we should say kind of for completion here. So in the next video, we're going to come back and we're going to now use all of these ideas and we're going to come up with a process of how we're going to just essentially add up a bunch of areas of rectangles, right? That's really what we're going to do. So we'll sort of solidify that process next time.